Picture a single point of light, so unimaginably brilliant that it outshines every star in its own galaxy, combined a beacon so powerful it can be seen from across the universe, a fire that has burned for billions of years. This is not science fiction. This is a quasar, the most luminous object in existence. And what if these cosmic lighthouses, these brilliant guides scattered through the void, are also the most profoundly bizarre phenomena we have ever encountered? What secrets do they hold that defy the very laws of physics as we know them? These are not calm, steady stars. Quasars and their broader family known as active galactic nuclei or AGN represent the hyperactive, violent hearts of distant galaxies. At their center lies an almost unimaginable engine, a supermassive black hole, a gravitational monster with the mass of millions or even billions of suns, greedily feeding on a swirling disk of gas and dust. It is this frenzied feast that unleashes enough energy to make a quasar shine with the light of 1 trillion suns, turning the core of a galaxy into the brightest thing for light years around. But the sheer power is only the beginning of the story. The true mystery of quasars lies in their strangeness, in the behaviors that leave even the most brilliant astronomers scratching their heads. We are about to embark on a journey into the deepest corners of space and time, to explore 25 of the most peculiar, puzzling, and downright inexplicable phenomena associated with these cosmic powerhouses. We will witness jets of matter screaming into space at nearly the speed of light, ponder brightness that flickers and changes in ways that seem physically impossible, and confront mysteries that challenge our most fundamental ideas about reality itself. This is a tour of the extreme, a look at the universe operating in a mode so intense it pushes the boundaries of what we thought was possible. So prepare to have your perspective shifted. This exploration is more than just a list of facts. It is an invitation to witness the universe in its most raw and energetic state. We will see how the study of these incredible objects doesn't just tell us about distant galaxies. It forces us to question and refine our understanding of gravity, matter, and energy right here at home. The journey through these 25 bizarre phenomena promises to be a humbling and awe-inspiring experience, revealing a cosmos far more dynamic, violent, and wonderfully strange than we ever could have imagined. Our journey into the bizarre begins with a phenomenon that, at first glance, seems to shatter one of the most fundamental rules of the cosmos. Einstein's theory of relativity established the speed of light as the universe's ultimate speed limit. Nothing with mass can ever reach it, let alone exceed it. Yet, when astronomers first trained their radio telescopes on the jets blasting out from quasars, they measured motions that appeared to do the impossible. They saw bright knots of material within these jets racing away from the central core at several times the speed of light. They called this superluminal motion, and its discovery sent shockwaves through the scientific community. How could our observations be so blatantly wrong? The answer is not a flaw in our instruments, but a breathtaking trick of geometry and physics playing out across cosmic distances. This illusion occurs because the jet of material is pointed almost directly at us. Imagine a single glowing blob of plasma ejected from the quasar at 99.9% the speed of light. As this blob travels through space, it emits light. The light it emits at the very start of its journey has a head start, but the light it emits a little later is being hurled toward us by the blob's own incredible velocity. Since the blob is moving almost directly along our line of sight, the later light almost catches up to the earlier light. From our distant vantage point, it appears as if the blob has covered a vast distance in an impossibly short amount of time, creating the perception that it is moving faster than light. It's a cosmic mirage, a relativistic effect that bends the rules of perception without actually breaking the universal speed limit. The confirmation of this explanation was a monumental achievement. It didn't just solve a puzzling observation, it provided powerful, indirect evidence for the entire model of active galactic nuclei. The only way to create such a precise and powerful jet, moving at such a staggering fraction of light speed, was through the incredible gravitational forces and magnetic fields generated by a supermassive black hole and its accretion disk. So, what initially seemed like a violation of physics turned out to be one of our strongest validations of it. This bizarre illusion ultimately cemented our understanding of the violent engines powering these distant beacons, proving that reality, even when it appears strange, always plays by its own profound rules. If the first phenomenon was a cosmic illusion, the second is a direct and relentless assault on our telescopes from across the universe. We now turn our attention to a specific and particularly violent class of active galaxy known as a blazar. The key to understanding a blazar lies in our perspective here on Earth. Remember those relativistic jets we just discussed? In a typical quasar, the jet might be pointed off at some angle into space. But a blazar is what happens when one of those jets, by pure cosmic chance, is aimed like a searchlight directly at our solar system. We are staring straight down the barrel of the most powerful particle accelerator in the universe. This unique vantage point makes blazars appear exceptionally bright across the entire electromagnetic spectrum, from radio waves all the way up to highly energetic gamma rays. But it also reveals one of their most baffling characteristics, a wild, unpredictable, and incredibly rapid flickering in their brightness. This is the blazar paradox. Astronomers have observed these objects doubling or even tripling in brightness over astonishingly short periods, sometimes in a matter of hours. To appreciate why this is so paradoxical, we need to think about the physics of light and causality. Nothing can travel faster than light, not even information. This means that for an object to change its brightness uniformly across its entire surface, a signal must have traveled from one side of the object to the other to coordinate the change. The maximum speed for that signal is light itself. Therefore, the shortest time scale over which an object can vary in brightness gives us a direct measurement of its maximum possible size. A change that happens over a few hours implies that the source of that brilliant, galaxy outshining light must be smaller than the distance light can travel in those few hours. This confines the incredibly powerful engine of a blazar to a region of space that is shockingly small, often no larger than our own solar system. We are left with a profound puzzle. How can such a tiny volume of space generate and release more energy than an entire galaxy of hundreds of billions of stars? The current models point to processes happening breathtakingly close to the event horizon of the supermassive black hole. Intense magnetic fields, twisted and amplified by the violently spinning accretion disk, are thought to funnel and accelerate particles to near light speeds, creating a concentrated, storm-like region of emission. The rapid flickering we see could be caused by shocks traveling through the jet or by turbulent magnetic reconnection events similar to solar flares on our Sun, but amplified to an almost incomprehensible scale. Observing a blazar is like watching the turbulent surface of a maelstrom from a great distance, where every ripple and eruption is magnified by the sheer power of the jet pointed directly at us. This direct line of sight forces us to confront the most extreme and energetic processes in the universe, happening on scales that challenge our very understanding of how matter and energy can behave. Now, let's move from the relativistic fireworks of jets to the inner workings of the engine itself. Deep within the heart of a quasar, just outside the event horizon of the supermassive black hole, lies the powerhouse, the accretion disk. This is a swirling, superheated maelstrom of gas and dust spiraling inward at fantastic speeds, and it's here that we encounter two more bizarre phenomena that reveal the complex dynamics of this cosmic whirlpool. The first of these is a peculiar feature in the quasar's light signature, something astronomers call double-peaked broad emission lines. To understand what this means, we need to think about the light emitted by the hot gas in the disk. Each chemical element emits light at specific characteristic wavelengths, like a fingerprint. For hydrogen gas in a quiet laboratory, this fingerprint is a single, sharp line. But in the frenzied environment of an accretion disk, this line becomes broad and blurry. Why? The answer lies with the Doppler effect, the same phenomenon that causes a siren's pitch to change as it passes by. Imagine the accretion disk as a gigantic, spinning carousel of glowing hydrogen gas. The gas on one side of the disk is spinning toward us at incredible velocities, while the gas on the opposite side is spinning away from us just as fast. From our distant viewpoint, the light from the gas moving toward us is squeezed or blue-shifted to a slightly shorter wavelength. The light from the gas moving away is stretched or redshifted to a slightly longer wavelength. The gas moving perpendicular to our line of sight doesn't shift at all. The net result is that the single, sharp emission line we would expect gets smeared out into a very broad, hump-shaped feature. But in some quasars, this hump doesn't look smooth. Instead, it shows two distinct peaks, one on the blue side and one on the red side. This double peak is the direct signature of a rapidly rotating disk. The two peaks come from the hottest and brightest parts of the disk, the regions moving directly toward and directly away from us at the highest speeds. It's a stunning confirmation that we are indeed seeing a vast, organized structure spinning under the immense gravitational pull of the black hole. But this orderly rotation is only part of the story. The incredible energy generated by friction and gravity within the disk doesn't just produce light, it also creates chaos. This brings us to our fourth phenomenon, powerful disk winds. Think of the accretion disk not just as a serene whirlpool, but as a hurricane. Amid the furious spinning, the intense radiation pouring out from the inner disk and the powerful magnetic fields twisting through the gas act like a cosmic hurricane wind. They can grab hold of material from the surface of the disk and violently hurl it outward, not in a focused jet but in a wide-angle torrent. These are quasar winds, and they can achieve mind-boggling speeds, sometimes reaching 20% of the speed of light. That's fast enough to travel from the Earth to the Sun in about 40 minutes. These winds are not a gentle breeze, they are a titanic force that can blow a huge bubble in the surrounding interstellar gas of the host galaxy. This process has profound implications far beyond the immediate vicinity of the black hole. For a long time, astronomers wondered why supermassive black holes aren't even larger than they are. Given the vast amount of gas available in a galaxy, you might expect these monsters to consume everything and grow without limit. Disk winds provide a compelling answer. They represent a powerful self-regulation mechanism. As a black hole feeds voraciously and its luminosity increases, the resulting radiation pressure can drive these immense winds, which effectively blow the very food supply away from the black hole's mouth. It's a cosmic feedback loop. The black hole eats, gets brighter, and then switches on a fan so powerful it clears its own dinner table. This wind can quench star formation across the entire galaxy by dispersing the raw material for new stars, effectively putting the brakes on the galaxy's growth. So, these bizarre spectral lines and violent outflows are far more than just curiosities. They are key to understanding the intimate and often stormy relationship between a black hole and its galactic home. Venturing even closer to the black hole's point of no return, we encounter a component so enigmatic that astronomers still debate its fundamental nature. This is the quasar's corona, a seething, ultra-hot region of plasma that hangs above and below the accretion disk like a celestial halo. While the disk itself glows white-hot, emitting mostly ultraviolet and optical light, the corona is a different beast entirely. It is a fog of particles heated to billions of degrees, so energetic that it shines brilliantly in X-rays. The exact process that creates this scorching environment is a major puzzle. One leading theory suggests that magnetic fields rising like loops from the turbulent disk can explosively reconnect, transferring immense energy to the surrounding gas, a process similar to what happens on our Sun, but amplified to an almost unimaginable scale. Another idea posits that the sheer violence of the disk's rotation creates frictional heating that boils material off its surface. The corona's geometry is equally mysterious. Is it a compact, flashlight-like source directly above the black hole, or is it a more extended, patchy structure enveloping the inner disk? The answer matters greatly because this corona is the primary source of the high-energy X-rays that we detect, and it plays a crucial role in illuminating the outer parts of the accretion disk, making them visible to us. It represents one of the most extreme and least understood environments in the universe, a ghostly, energetic shroud veiling the final moments before matter vanishes forever. This inherent instability and dynamism might hold the key to our next bizarre phenomenon, one that fundamentally challenges our static classification of these objects. For decades, astronomers sorted quasars into two main types. Type 1 quasars appear bright across all wavelengths, with strong, broad emission lines, suggesting we have a direct, unobstructed view of their blazing core. Type 2 quasars seem dimmer, with only narrow emission lines, as if a thick, donut-shaped ring of dust and gas, a structure called the torus, is blocking our view of the central engine. We assumed a quasar was simply one type or the other, a permanent feature of its architecture. Then we discovered changing-look quasars. These cosmic chameleons have been observed to transform dramatically, with a Type 1 quasar fading and its broad emission lines vanishing over just a few years, effectively turning into a Type 2. In some astonishing cases, the reverse happens, and a dim Type 2 suddenly flares up into a brilliant Type 1. This isn't a trick of perspective. It's a real, physical change happening on a timescale that, in cosmic terms, is lightning fast. What could cause such a radical metamorphosis? Two compelling theories are at the forefront. The first involves the black hole's appetite. If the rate of gas falling into the accretion disk suddenly drops, perhaps because a specific gas cloud has been fully consumed, the brilliant core could dim substantially. With less energy pouring out, the surrounding broadline region, which is made of clouds of gas that are heated and illuminated by the central engine, might simply cool down, recombine, and stop emitting the characteristic broadlines, causing them to disappear from our view. The second, even more dramatic, theory points to the obscuring torus itself. This dusty structure isn't necessarily a static ring. It could be a dynamic, clumpy fog. A dense knot of material drifting across our line of sight could, within a few years, randomly block our view, turning a Type 1 into a Type 2. Conversely, a clearing in the fog would reveal the hidden engine. The existence of changing-look quasars reveals that these cosmic giants are not steady, immutable beacons, but volatile and temperamental objects capable of profound transformation on a human timescale. To truly understand these rapid changes and probe the fine-scale structure of quasars, we need a tool of immense precision. Nature, in its ingenuity, provides one: quasar microlensing. This phenomenon relies on a cosmic alignment so perfect it acts as a natural telescope. When a distant quasar is perfectly aligned with a massive foreground galaxy, the gravity of that galaxy bends the quasar's light, creating multiple magnified images of the quasar around the galaxy's edge, an effect known as strong gravitational lensing. But within that foreground galaxy are countless individual stars. As these stars move through their orbits, they can pass directly in front of one of the magnified images of the quasar. Each star acts as its own tiny gravitational lens, causing a brief, additional brightening of that specific quasar image. This is microlensing. The true power of this effect lies in its selectivity. Because a single star is so small, it cannot magnify the entire quasar at once. Instead, it magnifies only a tiny part of it. As the star moves, it scans across different regions of the quasar's accretion disk. By meticulously measuring the changes in brightness and color during these microlensing events, astronomers can perform a kind of cosmic cartography. They can measure the size of the accretion disk at different wavelengths of light, confirming that the hotter, bluer light indeed comes from the smaller, hotter inner regions, while the redder light originates from the larger, cooler outer areas. In some cases, microlensing has even provided evidence for the size and structure of the broad line region, the area of glowing gas clouds surrounding the disk. It's a technique that transforms the faint, twinkling light of a distant quasar into a detailed map, allowing us to see structure on a scale that would otherwise be completely impossible to resolve, giving us an unprecedented close-up view of the very heart of darkness. Now we confront a puzzle so fundamental it challenges our understanding of how the largest structures in the universe evolve. This is the Final-parsec problem, and it begins with a seemingly straightforward scenario. Galaxies collide. We see this happening throughout the cosmos, and when two galaxies merge, their central supermassive black holes are drawn together by gravity, eventually forming a binary pair. At first, they spiral inward relatively easily as their immense gravity slingshots surrounding stars out of the way. But as the black holes get closer, a problem emerges. They need to shrink their orbit to a separation of about 1 parsec, roughly 3.26 light-years, to be close enough for gravitational wave emission to take over and complete the merger. This is the Final-parsec, and here, according to classical theory, the process should grind to a halt. The issue is one of supply and demand. To lose orbital energy and spiral closer together, the binary black holes need to interact gravitationally with other objects like stars. But within a sphere of influence just 1 parsec across, there are simply not enough stars to provide the necessary gravitational braking. The binary pair effectively clears out its neighborhood, creating a cosmic desert around itself. Once the available stars are ejected, the theory suggests the black holes would stall, remaining in a stable, everlasting dance, separated by that final parsec for a period far longer than the current age of the universe. This presents a glaring contradiction. If mergers are practically impossible, then the supermassive black holes we observe at the hearts of large galaxies, some of which are the products of previous mergers, should not exist. Even more compelling, gravitational wave observatories are now beginning to detect the ripples in space-time caused by these very mergers. The universe is clearly doing it, so what are we missing? Astronomers have proposed several fascinating solutions to this energetic impasse. One of the most promising involves the presence of vast amounts of gas. In a gas-rich galactic merger, the binary black holes are not orbiting in a vacuum. They are embedded within a dense, swirling accretion disk. As they move, they plow through this gas, creating gravitational drag. Think of it like wading through water. The resistance saps your energy and slows you down. For the black holes, this dynamical friction with the gas robs them of orbital energy, allowing them to spiral inward far more efficiently than by interacting with stars alone. The gas acts as a cosmic mediator, ensuring the final parsec is not an insurmountable barrier but a passable stretch of road. Another intriguing solution brings a third body into the dance. Imagine a single star wandering too close to the binary pair. The complex gravitational interplay can fling the star away at high speed, and in doing so, the star carries away a tiny bit of the binary's orbital energy. This is known as the gravitational slingshot effect. If a sufficient stream of stars can be funneled into the inner region, perhaps by a surrounding star cluster or a disrupted disk of material, this repeated process can gradually bleed away enough energy to drive the black holes together. It's a slow, steady trickle of energy loss that eventually culminates in a colossal collision. The detection of gravitational waves from such events is not just confirming that black holes merge, it is actively helping us test these very theories, providing real-world data on a process that was once purely theoretical. The Final-parsec problem reminds us that the cosmos often has creative solutions to the puzzles our equations create, using the dynamic interplay of gas, stars, and gravity to orchestrate the most violent and spectacular unions in the universe. Leaving behind the intricate dance of binary black holes, we now expand our view to a scale so vast it questions the very uniformity of the cosmos. One of the most deeply held assumptions in modern cosmology is the principle of homogeneity. This is the idea that, on the very largest scales, the universe is essentially smooth and uniform. If you were to look at a sufficiently large volume of space, the distribution of matter would look roughly the same no matter where you are. It's a foundational concept, but what if we found a structure so enormous that it seemed to break this rule? This is the startling possibility raised by the discovery of quasar superassociations, with the most famous example being a colossus known as the Huge-Large Quasar Group, or Huge-LQG. To grasp the sheer scale of this object, consider its dimensions. The Huge-LQG is not a cluster of galaxies, it is a cluster of quasars, the brightest and most active galactic nuclei. This structure contains 73 quasars and stretches across an astonishing 4 billion light-years at its greatest extent. To put that in perspective, our entire local group of galaxies, which includes Andromeda and the Milky Way, spans only about 10 million light-years. The Huge-LQG is 400 times larger. It is so immense that light, traveling at the universe's ultimate speed limit, would take nearly a third of the age of the universe just to go from one end to the other. According to our current understanding, the homogeneity of the cosmos should kick in at scales around 1.2 billion light-years. The existence of a single connected structure more than 3 times that size poses a direct challenge to this cosmological principle. The debate among astronomers is intense and fascinating. On one side, the discoverers of the Huge-LQG argue that the clustering of so many quasars in one region is incredibly unlikely to occur by random chance in a smooth universe. Quasars are not distributed evenly. They appear to be linked, tracing out the skeleton of a cosmic web on a scale we never thought possible. This suggests that the largest structures in the universe might be even larger than our models allow, implying that matter is clumpier on grand scales than we believe. If true, this would require a significant revision of our standard model of cosmology, potentially touching on our understanding of dark matter, dark energy, and the initial conditions of the Big Bang itself. The other side of the debate offers a more conservative but equally important explanation: statistical flukes. Critics point out that when you are surveying the entire observable universe, you are dealing with an enormous dataset. It is possible, they argue, that what we are calling a structure is simply a rare but statistically possible random clustering of quasars. Imagine rolling a dice thousands of times. You might occasionally get a long, surprising sequence of 6s. That doesn't mean the dice are loaded, just that probability allows for unusual runs to occur. The question becomes whether the Huge-LQG is a meaningful signal of new physics or just cosmic noise, an illusion of pattern in the vastness of space. Resolving this debate is an active area of research. Astronomers are now employing sophisticated statistical techniques and surveying even larger areas of the sky to see if such immense structures are truly rare anomalies or more common than expected. The outcome has profound implications. If quasar superassociations like the Huge-LQG are real physical entities, they would represent the largest organized structures ever identified, filaments in the cosmic web of breathtaking proportions. Their existence would force us to reconsider the limits of homogeneity and open a new chapter in our quest to understand the architecture of the universe on the grandest possible stage. This brings us to one of the most contentious and philosophically charged debates in modern astronomy, a controversy that strikes at the very heart of how we measure the cosmos. It all revolves around a simple yet profound observation: redshift. For nearly a century, we have understood that the light from distant galaxies is stretched to longer, redder wavelengths as it travels through an expanding universe. The greater the redshift, the farther away the galaxy is, and the faster it is receding from us. This cosmological redshift is the cornerstone of our entire picture of an expanding universe born from the Big Bang. But what if, for some of the most enigmatic objects like quasars, this fundamental ruler was broken? This is the core of the redshift controversy. The debate was ignited by observations made by astronomers like Holton Arp, who tirelessly catalogued peculiar galaxies. He presented photograph after photograph that seemed to show a quasar with a very high redshift, indicating it was billions of light years away, positioned suspiciously close in the sky to a much closer galaxy with a significantly lower redshift. In some cases, these quasars and galaxies even appeared to be connected by faint bridges of luminous material, or seemed to be aligned in ways that defied simple chance. Arp's most famous example is the galaxy NGC 4318, which has a jet-like appendage pointing directly toward a quasar with a much higher redshift. If the redshift truly indicated distance, this would be an impossible configuration. How could a quasar trillions of miles away be physically linked to a nearby galaxy? Arp and his supporters argued that these associations were not illusions. They proposed that the high redshifts of these quasars were not due to cosmic expansion at all, but were intrinsic, caused by some unknown physical property of the quasars themselves, perhaps related to their youth or extreme energy. This would mean these quasars were not distant cosmic beacons, but much closer objects ejected from the active nuclei of nearby galaxies, an idea that would completely upend our understanding of their power and scale. The mainstream astronomical community, however, has largely rejected this interpretation, relying on two powerful lines of evidence. The first is statistics. When you look at the entire sky, you see millions of galaxies and quasars. Simply by the laws of chance, some quasars will, by pure random alignment, appear very close to foreground galaxies from our vantage point on Earth. It's a classic case of a line-of-sight coincidence. Sophisticated statistical analyzers have repeatedly shown that the number of these apparent associations is no greater than what you would expect from random chance alone. What looks like a physical connection to the human eye searching for patterns is often just a trick of perspective across the immense depths of space. The second, and perhaps most definitive, counterargument comes from improved technology. The early photographic plates that Arp used were limited in their sensitivity. When the Hubble Space Telescope and other powerful observatories turned their gaze to these controversial pairs, they revealed a different story. Those faint filaments or bridges of light that seemed to connect a high redshift quasar to a low redshift galaxy were often revealed to be unrelated background structures or even image artifacts. In many cases, obtaining a precise spectrum of the connecting material showed that it shared the redshift of the foreground galaxy, not the quasar, meaning it was simply a faint part of the nearby galaxy that happened to point in the quasar's direction. There was no physical link. Furthermore, we have since observed quasars whose light passes through the outer halo of a foreground galaxy on its way to us. The intervening galaxy's gas imprints its own, lower redshift signature on the quasar's spectrum, providing direct, undeniable proof that the quasar is indeed far behind the galaxy, exactly as the cosmological redshift predicts. While the intrinsic redshift hypothesis is not part of mainstream cosmology today, the controversy served an invaluable purpose. It forced astronomers to be more rigorous in their analysis, to question their assumptions, and to seek ever more precise observations. It highlights the essential, self-correcting nature of science, where even compelling visual evidence must bow to the stricter tests of statistical probability and technological verification. The resolution of this debate ultimately reinforced, rather than overturned, our confidence in the expanding universe model. But it stands as a powerful reminder of how easily our perceptions can be deceived by the vast and wondrous complexity of the cosmos. Now, if we dare to peer even closer to the precipice of the black hole itself, we encounter a subtle but incredibly powerful spectral signature written in the language of X-rays. This phenomenon revolves around a specific heavy element, iron. In the chaotic environment of an active galactic nucleus, iron atoms in the swirling accretion disk are constantly bombarded by the intense X-ray radiation from the hot corona above. This bombardment knocks electrons out of their inner orbits, and when other electrons fall in to fill the void, they emit light at a very specific high-energy wavelength, a distinct fingerprint known as the iron K-alpha line. In a calm laboratory setting, this fingerprint would appear as a single, sharp spike on a graph, but around a supermassive black hole, the line is anything but sharp. It becomes incredibly broad and distorted, smeared out into a bizarre, asymmetrical profile that holds direct clues about the most extreme gravitational environment we can observe. The key to this distortion lies in a combination of two of Einstein's most profound predictions. The first is the Doppler effect, which we encountered with the double-peaked lines from the disk. Gas on the side of the disk spinning toward us emits its iron line light at a slightly higher energy, while gas spinning away emits at a slightly lower energy. This smears the single line into a broader hump, but the second effect is even more dramatic and unique to such intense gravity, gravitational redshift. As the X-ray photons struggle to climb out of the black hole's immense gravitational well, they lose energy. The closer to the event horizon the light is emitted, the more energy it loses. This stretches the wavelength of the light, shifting it toward the red, lower energy end of the spectrum. The combination of these effects creates a truly anomalous iron line. The side of the disk moving toward us should produce a blue-shifted, high-energy peak, but for the gas closest to the black hole, the gravitational redshift is so overpowering that it cancels out and even reverses this blue shift. The result is a pronounced and extended red wing, a long, sloping tail on the iron line that stretches far down into lower energies. This red wing is our most direct window into the dynamics of matter orbiting just outside the event horizon. By carefully analyzing its shape, astronomers can essentially map how fast the inner accretion disk is spinning. They can probe regions where space-time itself is being dragged around by a rotating black hole, an effect known as frame dragging. The extreme broadening of the line tells us that we are seeing light emitted from a region where orbital velocities are a significant fraction of the speed of light, and where gravity warps the very fabric of reality. This makes the iron line far more than just a spectral curiosity. It is one of the few practical tools we have for testing Einstein's theory of general relativity in what is called the strong field regime. Most tests of relativity, like the precise orbits of Mercury or the timing of GPS satellites, occur in the weak field limit where gravity is relatively mild. The environment around a black hole is the ultimate strong field laboratory, where gravity is so intense that the predictions of general relativity become extreme. The anomalous iron line provides a way to check if Einstein's equations still hold up under these most violent conditions. Any deviation from the predicted shape of the line could be a hint of new physics, a sign that our understanding of gravity needs to be revised in the face of such overwhelming power. So, by deciphering the subtle, skewed signal of iron atoms screaming around a black hole, we are not just studying a distant object, we are conducting a fundamental experiment on the nature of space, time, and gravity itself. Having charted the immense outer structures and probed the deepest relativistic realms, we now arrive at a mystery that connects the very smallest to the very largest scales in the cosmos. This phenomenon is not about a single, bizarre object, but about a stunningly precise cosmic relationship, one that links the silent, dark heart of a galaxy to the shining body of stars that surrounds it. For a long time, astronomers assumed that a supermassive black hole was just a feature of a galaxy, like a city having a large central park. The size of the park and the size of the city might be loosely related, but one didn't necessarily control the other. Then, in the late 1990s, as measurements improved, a shocking pattern emerged. They discovered that the mass of a galaxy's central black hole is not random. It is locked in a tight, mathematical embrace with the properties of the galaxy's central bulge, the dense, spherical swarm of stars at its core. The most famous of these is the M-sigma relation. It states that the mass of the black hole, M, is directly proportional to the velocity dispersion, sigma, of the stars in the bulge. Velocity dispersion is a measure of how fast the stars are randomly zipping around within the bulge. A higher sigma means the stars are moving faster, which in turn indicates a stronger gravitational field holding the bulge together. The correlation is incredibly tight. A galaxy with a bulge where the stars are moving twice as fast will, with remarkable predictability, host a black hole that is roughly 8 times more massive. This isn't a loose trend. It's a precise rule that holds true across a vast range of galaxy sizes, from small galaxies with black holes of a few million solar masses to the giants with black holes weighing billions of suns. This discovery was profound. It means that if you simply measure the random motions of the stars in a distant galaxy's bulge, you can accurately predict the mass of the invisible monster lurking at its center, an object that is a billion times smaller in size. It's as if the shadow an object casts is perfectly proportional to the object itself, even though the shadow is enormous and the object is tiny. This bizarre scaling relation suggests a deep, fundamental connection between the growth of the black hole and the growth of its host galaxy, a connection that defies their vast difference in scale. This revelation immediately presented astronomers with a classic cosmic chicken or egg problem. Which came first? Does the galaxy build the black hole, or does the black hole build the galaxy? Two compelling but opposing theories have been battling it out for decades. The first theory is often called bottom-up growth. In this scenario, the galaxy forms first. As gas collapses to build the galactic bulge, some of that gas naturally funnels down to the very center, feeding the black hole. The black hole's growth is therefore a passive consequence of the galaxy's growth. It simply eats what it's given. The correlation exists because both the black hole and the bulge are fed from the same reservoir of gas. The more gas available to make stars and build the bulge, the more gas is available to feed the black hole. In this view, the black hole is a passive passenger on the galactic journey, its mass scaling with the galaxy's development but not actively influencing it. The second, and now more favored, theory proposes a much more active and dramatic relationship. This is the idea of self-regulation through feedback. Here, the black hole is not a passive eater, it is an active governor. Imagine the black hole and the galaxy growing together. As the black hole feeds, it becomes an active galactic nucleus, unleashing tremendous energy in the form of radiation and those powerful jets and winds we discussed earlier. This outpouring of energy acts like a cosmic thermostat. It heats up the surrounding gas, preventing it from cooling and collapsing to form new stars. In extreme cases, the quasar winds can even blow the galactic gas reservoir clean away. This feedback process effectively shuts off the black hole's own food supply. A more massive black hole produces more powerful feedback, which can quench star formation in a larger galaxy. A smaller black hole has gentler feedback, allowing a smaller galaxy to form. In this model, the black hole actively regulates the growth of its own host, establishing an equilibrium that results in the tight correlation we observe. The black hole grows until it becomes powerful enough to shout down the galaxy, telling it to stop growing. It's a violent, self-limiting symbiosis that explains why we don't see galaxies with puny black holes or supermassive black holes living in tiny galaxies. The two are forced into balance by a cycle of feeding and feedback. This concept of a self-regulating black hole brings us directly to one of the most pivotal and powerful roles quasars play in the cosmic story: quasar feedback. We've seen how these objects are brilliant beacons, but their true cosmic significance extends far beyond their light. They are not just passive inhabitants of their galaxies, they are active, often violent architects. Quasar feedback is the process by which the incredible energy unleashed by an active galactic nucleus directly impacts its entire host galaxy, shaping its destiny in profound and irreversible ways. The primary mechanism for this is through the immense outflows we touched on earlier, the powerful winds and relativistic jets. These aren't merely byproducts of the black hole's feast, they are transformative forces. Consider the lifeblood of any galaxy, cold, dense gas. This is the raw material from which new stars are born. For a galaxy to remain vibrant and form new generations of stars, it needs a steady supply of this cold gas collapsing under its own gravity. Now imagine turning on a quasar. The radiation pouring out from the accretion disk is so intense that it slams into the surrounding galactic gas. This radiation pressure can push the gas away, but the more dramatic effect comes from the actual physical outflows. The quasar-driven winds, which can reach speeds of thousands of kilometers per second, act like a cosmic hurricane, plowing through the galaxy's reservoirs of star-forming fuel. This does two things. First, it simply blows the gas away, ejecting it entirely from the gravitational grasp of the galaxy. Second, and perhaps more subtly, it violently heats the remaining gas. Instead of being cold and dense, ready to collapse, the gas becomes hot and diffuse like a thin, high-pressure fog. In this state, it cannot form stars. This process is known as quenching. The galaxy, once a stellar nursery, is effectively sterilized. Its star formation is shut down. This feedback loop solves a major puzzle in astronomy. Why are there so many large, old, red and dead elliptical galaxies in the universe? These galaxies are dominated by aging red stars and show no signs of ongoing star formation. They seem to have used up their gas long ago. Quasar feedback provides a compelling explanation. During a merger event, when two gas-rich galaxies collide, vast amounts of gas are funneled toward the center, triggering a furious burst of star formation and feeding the supermassive black hole, igniting a quasar. The quasar then unleashes its fury, blowing away or heating up the very gas that was fueling both the starburst and its own growth. It's a spectacular act of self-sabotage that brings a sudden, dramatic end to the galaxy's most active period of growth. The quasar, having cleared its own dinner table, eventually fades as its fuel supply is cut off, leaving behind a quiescent galaxy that slowly reddens over billions of years. In this way, the brilliant, short-lived phase of a quasar acts as the closing chapter in a galaxy's vibrant youth, transitioning it into a stable but stagnant old age. This intimate connection between the smallest point, the black hole, and the largest structure, the galaxy, is a cornerstone of modern models of galaxy evolution, showing that you cannot understand the life of a galaxy without understanding the monster at its heart. This elegant solution to the diversity of active galaxies is known as the AGN unification model, and its beauty lies in its sheer simplicity. For decades, astronomers were puzzled by the zoo of different objects they were cataloging. There were quasars, incredibly luminous but often distant. There were Seyfert galaxies, closer and less powerful, but with similar bright nuclei. There were radio galaxies with giant lobes, and of course the violently variable blazars. The question was, were these fundamentally different kinds of beasts, or were they different manifestations of the same underlying creature? The unification model proposes the latter. It suggests that the primary reason for all this diversity is not a difference in the engine itself, but a simple trick of perspective, where we, the observers, happen to be sitting in relation to the cosmic machinery. At the heart of this model is a single, universal structure. Imagine a supermassive black hole, its accretion disk, and its super-hot corona, just as we've described. But surrounding this inner engine is a thick, donut-shaped ring of gas and dust called the torus. This isn't a solid object, but a dense, clumpy cloud that extends for light years. Now the key is that this torus is opaque. It blocks our line of sight. Whether we see a brilliant quasar or a dimmer, obscured nucleus depends almost entirely on our viewing angle relative to this central torus. If we are fortunate enough to have a direct face-on view, looking straight down the pole of the system, we get an unobstructed view of the blazing accretion disk and the broad line region of hot gas clouds swirling just outside it. This is what we classify as a Type 1 active galactic nucleus. We see the full, dazzling power of the engine, and its spectrum shows both broad and narrow emission lines. A quasar is essentially the most luminous version of this, a Type 1 AGN at its most extreme. But now, tilt your perspective. If we view the system from the side, looking through the plane of the dusty torus, our view of the bright central engine is completely blocked. We cannot see the accretion disk or the broad line region directly. All we can see is the more distant narrow line region, which lies outside the torus and is therefore visible from all angles. This is what we classify as a Type 2 AGN. It appears much dimmer because the brilliant core is hidden and its spectrum shows only narrow emission lines. This simple geometric switch explains the fundamental difference between Type 1 and Type 2 objects, but the model goes even further to unify other members of the AGN family. Remember the blazar, that extraordinarily violent and variable object. In the unification scheme, a blazar is simply a Type 1 AGN where our view is not just unobstructed, but we are looking directly down the throat of one of its powerful relativistic jets. We are staring into the cosmic blowtorch itself. The incredible brightness and variability are due to the jet's emissions being Doppler boosted because it's pointed right at us. Conversely, a radio galaxy with giant lobes is often a Type 2 AGN seen from the side, where the jets are plowing into the intergalactic medium, creating those vast radio-emitting structures, but the central engine is hidden from our view. The power of the unification model is that it takes a seemingly chaotic menagerie of objects and arranges them into a single, coherent family portrait. It tells us that the difference between a brilliant quasar that can outshine a galaxy and a quieter, obscured Seyfert galaxy might be nothing more than an accident of cosmic orientation. This doesn't mean all AGN are identical. Their black hole masses, accretion rates, and host galaxies certainly differ, but the unification model provides the fundamental framework, the basic blueprint, that explains the primary observed differences through the simple yet profound geometry of our viewpoint. It's a powerful reminder that in astronomy, perspective is everything, and what appears to be a collection of unique monsters may in fact be a single species, seen from every possible angle. But sometimes the orderly process of galactic evolution is violently interrupted by a cataclysm of almost unimaginable scale. We now turn to one of the most dramatic and fleeting events in the cosmos, the tidal disruption event. Picture a star much like our own sun, orbiting peacefully in the quiet outskirts of a galaxy. Its trajectory, by sheer chance or the subtle gravitational nudges of other stars, sends it on a fateful plunge toward the central supermassive black hole. For most of its journey, the star is safe, held together by its own powerful gravity. But as it crosses a critical threshold known as the tidal radius, the black hole's gravitational grip becomes overwhelming. The force of gravity pulling on the side of the star closest to the black hole is vastly stronger than the force pulling on the far side. This difference, the tidal force, stretches the star horizontally while compressing it vertically, pulling it apart into a long, thin stream of gas in a process whimsically called spaghettification. In a matter of hours, a star that has shone steadily for millions or billions of years is utterly shredded. The destruction of the star, however, is only the beginning of the spectacle. The stellar debris does not simply vanish into the black hole. Instead, it is flung onto a variety of chaotic orbits. Roughly half of the gas is ejected from the system entirely, while the other half forms a swirling, temporary accretion disk around the black hole. This sudden, massive injection of fresh fuel ignites a brilliant flare of radiation that can outshine the entire host galaxy for weeks or even months. This is the tidal disruption flare, a beacon signaling the death of a star and the brief awakening of a dormant black hole. The light curve of this flare, how its brightness changes over time, follows a distinctive pattern. It rises sharply to a peak as the debris falls in most rapidly, and then gradually fades away as the remaining gas is consumed, following a predictable rate of decline. This predictable fade allows astronomers to confidently identify these events amidst the countless other sources of light in the sky. The true value of a tidal disruption event lies in its role as a perfect natural experiment. In galaxies where the central black hole is dormant, not actively feeding, it is incredibly difficult to detect and measure. It sits in darkness, its presence only inferred from its gravitational influence on surrounding stars. A tidal disruption event changes everything. It lights up the black hole's immediate environment, providing a direct probe of its properties. By analyzing the spectrum and evolution of the flare, astronomers can accurately estimate the mass of the black hole. The duration and brightness of the event are directly tied to the gravity of the central engine. Furthermore, these events offer a unique opportunity to study the fundamental process of accretion, how matter falls into a black hole from its very beginning. Unlike persistent quasars, which are fueled by a steady, long-term supply of gas, a tidal disruption event shows us accretion starting from scratch with a known amount of fuel, the remains of a single star. This allows scientists to test theories of accretion physics in a clean, controlled manner that would be impossible to replicate. Each time a star is torn apart, it provides a short-lived but incredibly detailed laboratory for understanding the most extreme gravitational environments in the universe. While the violent demise of a star in a tidal disruption event gives us a brief, brilliant window into a single black hole, quasars themselves offer a far more sweeping and enduring utility. Their phenomenal, steady luminosity turns them into the ultimate cosmic lighthouses. Imagine you are an astronomer trying to study the faint, wispy gas clouds that float in the vast emptiness between galaxies. These clouds are the raw material of the cosmic web, the invisible scaffolding upon which galaxies are built, but they are so diffuse they emit almost no light of their own. Trying to observe them directly is like trying to see a faint puff of smoke in a dark room. But if you could place a brilliant light source behind that smoke, its silhouette and structure would suddenly become visible. This is precisely the role quasars play on a universal scale. Their light, traveling for billions of years across the cosmos, acts as a perfect backlight, illuminating everything that lies in its path. As this brilliant beam journeys toward us, it passes through countless clouds of hydrogen gas, both within distant galaxies and in the truly intergalactic void. When the light hits these clouds, the gas doesn't just block the light. It acts like a filter, absorbing specific wavelengths that correspond to the energy needed to excite its atoms. For hydrogen, the most common element, this creates a characteristic absorption line at a very specific wavelength in the ultraviolet part of the spectrum. But because the universe is expanding, the light from the quasar is stretched or redshifted during its long journey. The further away the gas cloud is, the more the light has been redshifted by the time it reaches us. The result is a quasar spectrum, which should be a smooth, continuous curve of light, instead becoming a forest of absorption lines. Each dark line in this Lyman alpha forest, named for the specific hydrogen transition, corresponds to a different cloud of gas at a different distance along the line of sight. It's as if we have a core sample of the universe, with each line representing a different layer in cosmic history. By analyzing this forest, astronomers can do more than just count clouds. They can measure their density, their temperature, and even their motion, building a three-dimensional map of the large-scale structure of the cosmos. This technique becomes even more powerful when we encounter a particularly dense wall of gas, an entire galaxy or a massive protogalactic cloud that lies directly between us and the quasar. These systems create not just a single line, but a whole series of absorption lines from many different elements: hydrogen, carbon, silicon, oxygen, and iron. This pattern is known as a damped Lyman alpha system, and it is like finding a fossilized snapshot of a galaxy in its youth. Because the light from the quasar is so ancient, we are seeing these absorbing galaxies not as they are today, but as they were billions of years in the past. By studying the chemical composition revealed by these absorption lines, we can trace the history of star formation across cosmic time. The presence of heavy elements like iron tells us that stars have already lived and died in that galaxy, seeding the gas with the elements forged in their nuclear furnaces. A system with very few heavy elements might be a truly primordial cloud, a building block that has yet to form many stars. In this way, a single quasar's beam of light becomes a time machine, allowing us to take a detailed chemical census of galaxies across 9/10 of the universe's history, all without ever having to see the galaxies directly. These cosmic lighthouses therefore illuminate not just the structure of space, but the very evolution of matter itself, revealing how the simple elements born in the Big Bang were progressively enriched into the complex chemistry that makes our own world possible. Moving from the violent chaos of tidal disruptions to the underlying order of quasar physics, we encounter a principle that brings a remarkable sense of organization to their apparent diversity. After cataloging so many bizarre and extreme behaviors, it might seem that quasars are a collection of unique individuals, each with its own peculiarities. But what if there was a master key, a unifying framework that could sort this cosmic zoo into a coherent family tree? This is the ambition of the quasar main sequence, a powerful diagnostic tool that does for active galactic nuclei what the Hertzsprung-Russell diagram did for stars. It reveals that beneath the wild variations in brightness and spectral features lies a deep and elegant order, governed by just two fundamental properties of the central engine. The diagram itself is a plot, but the story it tells is one of physical cause and effect. On one axis, we typically find a measure of the relative strength of certain emission lines, particularly those of iron and oxygen. This ratio acts as a probe for the shape of the quasar's spectral energy distribution, essentially, how its brightness is distributed across different wavelengths from ultraviolet to X-rays. On the other axis, you might find a parameter related to the width of the broad emission lines, which connects to the velocity of the gas clouds in the broad line region, and by extension to the black hole's mass and the accretion rate. The true power of the diagram emerges when you plot thousands of quasars. They don't scatter randomly across the graph. Instead, they arrange themselves along a well-defined sequence, a curved track that reveals a continuum of quasar properties. At one end, you find sources with strong, blue-shifted emission lines, indicating powerful winds and very bright X-ray emission relative to their ultraviolet light. At the other end, quasars have weaker winds, different line shapes, and a much quieter X-ray corona. This isn't a random assortment, it's a smooth progression. So, what are the two master knobs that control where a quasar sits on this sequence? The first is the accretion rate relative to the Eddington limit. The Eddington limit is the theoretical maximum luminosity a black hole can achieve before the outward pressure of its own radiation overwhelms the inward pull of gravity, effectively blowing away its fuel supply. A quasar accreting at a high fraction of this limit, say 50% or more, is in a state of frenzy, consuming matter as fast as physics will allow. This intense feeding leads to a puffed-up, very bright accretion disk and drives powerful radiation-driven winds, placing it at one specific part of the main sequence. Conversely, a black hole feeding at a much more sedate pace, perhaps only 1% of its Eddington limit, will have a cooler, dimmer disk and gentler outflows, situating it at a different point on the sequence. The accretion rate fundamentally changes the structure and dynamics of the entire system. The second governing parameter is the innate shape of the spectral energy distribution, which is thought to be tied to the black hole's spin. A rapidly rotating black hole can release far more energy from its accretion disk and is capable of generating much more powerful magnetic fields that can launch and collimate relativistic jets. This influences the balance between the thermal ultraviolet light from the disk and the non-thermal X-rays from the corona. A high-spin black hole might produce a much stronger X-ray corona, which in turn affects how it ionizes the surrounding broadline region, changing the relative strengths of the emission lines we observe. The interplay between these two factors, how fast the black hole is eating and how fast it is spinning, creates the spectrum of observed quasar types. The main sequence diagram is therefore not just a classification scheme, it is a physical theory in graphical form. It tells us that the incredible diversity of quasars is not random chaos but the predictable outcome of a few simple variables, allowing astronomers to look at a quasar's spectrum and immediately infer the fundamental state of its central engine, turning a bewildering menagerie into an orderly and understandable family. This orderly progression along the quasar main sequence gives us a powerful framework for understanding black holes across a vast range of masses and activities. But this very framework leads us directly to one of the most perplexing gaps in our cosmic senses, a missing link in the life cycle of these gravitational giants. We have confidently observed black holes at two extremes. On one end, we have stellar mass black holes, the remnants of massive stars, weighing in at between about 5 and 100 times the mass of our Sun. On the other end, we have the supermassive black holes, the monsters at the centers of galaxies, with masses ranging from millions to billions of solar masses. This presents a glaring, logical question. How do you get from one to the other? The journey from 100 solar masses to 1,000,000 must involve a middle stage, a population of so-called intermediate mass black holes, or IMBHS, weighing between 1,000 and 100,000 solar masses. Yet, finding clear, unambiguous evidence for these middleweights has proven to be one of astronomy's most stubborn challenges. The existence of these objects is not just a matter of neat categorization, it's central to our understanding of cosmic evolution. The supermassive black holes we see in the very early universe, just a few 100 million years after the Big Bang, are already colossal. For them to have grown so massive so quickly, they must have started from substantial seeds. They couldn't have grown from a single stellar mass black hole alone, as there simply isn't enough time for that slow, steady accretion. Intermediate mass black holes are the leading candidates for these seeds. They could have formed in the dense, chaotic environments of the first star clusters, where direct collisions and mergers of massive stars might have created a hefty progenitor. Alternatively, they could have collapsed directly from immense clouds of primordial gas in the early universe. If we can find these IMBHS today, especially in dwarf galaxies which are considered the modern-day equivalents of the universe's first galaxies, it would be like finding a living fossil, a relic from the dawn of structure formation. Their apparent absence is therefore a major puzzle. The hunt for these elusive objects has focused on a few promising leads. One of the most compelling is the study of ultra-luminous X-ray sources, or ULXS. These are objects located within galaxies, but far from the galactic center, that glow with an incredible brilliance in X-rays, often exceeding the theoretical limit for a stellar mass black hole accreting at a steady rate. This Eddington limit, as we discussed, is the point where radiation pressure pushes back against gravity. If a ULX is truly a single object and not a cluster of fainter sources, its extreme luminosity suggests it must be powered by a black hole larger than the stellar mass variety, an intermediate mass black hole that is feeding at a rapid pace. However, the case is not closed. An alternative explanation is that these are indeed stellar mass black holes, but they are somehow breaking the Eddington limit, perhaps through a process called beaming, where their emissions are focused into a narrow jet that by chance is pointed directly at us, making them appear brighter than they truly are. Distinguishing between these scenarios requires painstaking observations to measure the mass of the compact object, a difficult task when it's not at a galaxy's center. Another highly promising hunting ground is the nucleus of small dwarf galaxies. Every large galaxy like our Milky Way was built up from the mergers of smaller dwarf galaxies. If the correlation between galaxy bulge mass and black hole mass holds true even at these small scales, then dwarf galaxies should host correspondingly smaller central black holes perfectly within the intermediate mass range. Searching for these requires detecting the faint signs of accretion in galaxies that have very low overall luminosity. Astronomers look for the subtle spectroscopic signatures of a low-luminosity active galactic nucleus, faint broad emission lines, or the telltale glow of hot gas. In recent years, there have been several tantalizing discoveries. For instance, the dwarf galaxy called RMC 136 appears to host a black hole of about 50,000 solar masses, and the object known as HLX-1 in another galaxy was a strong candidate before fading from view. Each potential detection is a major event, but confirming them beyond doubt is a challenge. The accretion signature can be weak and intermittent, and it can be difficult to rule out other phenomena, like a concentrated cluster of massive stars. The difficulty in finding these middleweights might itself be a crucial clue. It could be that intermediate mass black holes are inherently quiet, spending most of their time in a dormant state with little gas to feed on, making them exceptionally difficult to detect. Their formation might also be a rare event, occurring only under very specific conditions in the early universe. Alternatively, their dynamical evolution might be self-limiting. In a dense star cluster, an IMBH could be ejected entirely through gravitational interactions, flung out into the intergalactic void as a rogue black hole, forever invisible to our telescopes. The ongoing search is pushing the limits of our technology, combining data from X-ray, optical, and radio observatories to build a compelling case for each candidate. The upcoming deployment of more powerful instruments will be crucial. The ability to detect the gravitational waves from the merger of two IMBHs would be the definitive proof, a direct measurement of their mass that bypasses the uncertainties of interpreting light. Finding this missing link is more than just filling a gap in a chart. It is about completing the origin story of the supermassive black holes that shape galaxies, and in doing so, better understanding our own place in the hierarchical growth of the cosmos. But sometimes the direct path to the truth is blocked, forcing us to rely on clever tricks of observation to see what would otherwise remain hidden. This brings us to a phenomenon that acts like a cosmic periscope, allowing us to peer around corners and into the most obscured regions of an active galactic nucleus, the study of polarized light. To understand this, we first need to grasp what polarization means. Ordinary light, like that from the sun or a light bulb, is a chaotic mix of electromagnetic waves vibrating in every direction perpendicular to its path. Polarized light, however, is light whose waves have been organized, forced to vibrate predominantly in a single plane. This can happen through several mechanisms, but for quasars, the two most important are scattering and synchrotron radiation, and each reveals a different piece of the puzzle. For those active galaxies where our view is blocked, the Type II AGN hidden behind their thick, dusty torus polarization provides a crucial backdoor. Imagine trying to look directly at a brilliant lighthouse lamp during a dense fog. The direct beam is blinding and obscured, but if you look at the light reflecting off the fog droplets around the lighthouse, you can get a good sense of the lamp's brilliance and color. This is precisely how polarization helps us study obscured quasars. The intense light from the hidden central engine, the accretion disk and broad line region cannot reach us directly. However, some of that light travels upward out of the plane of the torus and scatters off clouds of electrons or dust grains located above and below the obscuring ring. This scattering process polarizes the light. When astronomers analyze the faint, scattered light coming from around the galaxy's core, they can isolate this polarized component. And within that polarized light, they often find the spectral fingerprints, the broad emission lines that are completely absent from the direct, unpolarized light we receive. It's a spectacular confirmation of the unification model. We are not seeing the central engine itself, but its reflection, its ghostly imprint, scattered off surrounding material and cleverly decoded through the physics of polarization. This technique has been instrumental in proving that many seemingly dull galactic nuclei are in fact hiding brilliant quasars behind a cosmic veil. The second major clue from polarization comes from the jets themselves. The incredibly energetic particles spiraling along the magnetic field lines within these jets emit light through a process called synchrotron radiation. This emission is inherently highly polarized. The degree and angle of this polarization act as a direct probe of the magnetic field structure at the heart of the jet. If the magnetic field is a tangled, chaotic mess, the polarization will be weak and random. But if the field is highly ordered, like a vast, organized bundle of wires running along the jet's length, the polarization will be strong and its angle will reveal the field's orientation. Observations consistently show strong polarization in quasar jets, indicating the presence of these powerful, large-scale magnetic fields. This is crucial evidence for the theory that these fields are not just a byproduct of the jet, but are fundamental to its very formation and collimation. They act like a straitjacket, confining and directing the relativistic plasma into a narrow, focused beam that can punch through intergalactic space for millions of light years. By mapping how the polarization changes along the length of the jet, astronomers can even trace how these magnetic fields evolve and interact with their surroundings, revealing the dynamic physics of these cosmic accelerators in action. Our journey through the bizarre now takes us from the grandest scales of cosmic structure down to the very smallest, most energetic particles imaginable. We leave behind the polarized light and hidden quasars to confront a mystery that arrives at Earth from the depths of intergalactic space: ultra-high-energy cosmic rays. These are not rays of light, but atomic nuclei, protons, or the nuclei of heavier elements like iron, traveling at a fraction of the speed of light and carrying an amount of kinetic energy that is almost incomprehensible. We are talking about particles with energies exceeding 100 million trillion electron volts. To put that in perspective, that is millions of times more energy than what the most powerful particle accelerator on Earth, the Large Hadron Collider, can impart to a single proton. When one of these cosmic bullets strikes the top of our atmosphere, it triggers a massive cascade of secondary particles, a sprawling air shower that can cover dozens of square kilometers. The existence of such particles is a profound puzzle. What natural engine in the universe could possibly accelerate a single, tiny particle to such an extreme? For decades, one of the leading candidates has been the most powerful engines we know of, the relativistic jets shooting from active galactic nuclei. The conditions within these jets are uniquely suited to this incredible task. Theorists propose a mechanism called Fermi acceleration, or diffusive shock acceleration. Imagine a proton wandering into the turbulent, magnetized environment of a quasar jet. It bounces back and forth across a shock wave traveling through the jet, much like a surfer being pushed back and forth by the waves near the shore. With each crossing, the magnetic fields in the shock front give the particle a slight boost in energy. Over many, many cycles, this process can gradually accelerate the proton to these astronomical energies, eventually flinging it out into intergalactic space like a cosmic slingshot. The immense power and size of AGN jets provide both the raw energy and the vast distance needed for this gradual acceleration to reach its ultimate limits. However, this idea runs headlong into a major theoretical barrier known as the Greisen-Zatzeping, Kuzmin cutoff or GZK cutoff. This is not a limit on the acceleration process itself, but on how far such an ultra-high-energy particle can travel through the universe. Space is not a perfect vacuum. It is filled with the faint relic radiation from the Big Bang, known as the cosmic microwave background. This background radiation is a sea of low-energy photons that permeates all of space. For a proton traveling with an energy above a certain threshold, about 100 million trillion electron volts, this harmless background radiation transforms into an impenetrable wall. From the proton's ultra-relativistic perspective, the microwave background photons are dramatically blue-shifted, appearing as a barrage of high-energy gamma rays. When one of these blue-shifted photons collides with the ultra-high-energy proton, it can trigger a reaction that creates new particles, most notably a pion. This interaction robs the proton of a significant portion of its energy. Over a long journey, these repeated collisions act like a form of interstellar friction, sapping the energy of any proton that tries to travel too far. The theoretical calculation shows that a proton starting above the GZK energy should be slowed down below that threshold within a travel distance of about 150 million light-years. This distance defines our local cosmic neighborhood, known as the GZK horizon. This creates a fascinating and controversial puzzle for astronomers. If the GZK cutoff is real, then any ultra-high-energy cosmic ray we detect must have originated from a source within 150 million light-years of Earth. When researchers trace back the tentative paths of these particles, their directions often seem to point back toward locations where we see active galactic nuclei. This would be a beautiful, self-consistent picture. AGN jets within our local universe are the accelerators, and the GZK cutoff explains why we don't see such particles from more distant quasars. The problem is, when we look around our local cosmic volume, we don't see many powerful, jet-producing AGN that seem capable of this feat. The most famous potential source, the giant elliptical galaxy Messier 87 with its spectacular jet, is certainly within the horizon, but the number of such obvious candidates is small. This has led to an intense debate. Is our understanding of the GZK process incomplete? Could there be other, more exotic sources like gamma-ray bursts or even decays of super-heavy particles from the early universe? Or does this apparent shortage of local sources suggest that the acceleration mechanisms in AGN jets are even more efficient and prevalent than we thought, operating in quieter galaxies we haven't yet identified as cosmic ray powerhouses? The detection of these rare, ultra-high-energy particles, therefore, does more than just break energy records. It serves as a direct probe of both the most violent astrophysical environments and the fundamental properties of the universe itself, testing our models of particle physics and cosmic structure on the very largest scales. But the quest to understand the engines of active galactic nuclei leads us to an even deeper mystery, one that involves the most elusive substance in the universe. For all their brilliance, quasars and their kin are powered by ordinary matter, the protons, neutrons, and electrons that make up stars, planets, and us. Yet, we know this familiar matter accounts for less than 20% of the total gravitational pull holding galaxies together. The rest is the invisible grip of dark matter. This leads to a fascinating and highly speculative question. Could these two cosmic mysteries, active galactic nuclei and dark matter, be secretly intertwined? This is the provocative idea behind the dark matter annihilation hypothesis, a theory that suggests the incredible environments around supermassive black holes might be natural traps for dark matter, turning the hearts of galaxies into powerful dark matter detectors. The logic begins with gravity. Dark matter, whatever it is, interacts gravitationally. We believe it forms vast, diffuse halos around galaxies. At the very center of that halo, sitting at the bottom of the galaxy's gravitational well, is the supermassive black hole. Theorists propose that over billions of years, the black hole's immense gravity would slowly pull in dark matter particles from the surrounding halo, creating an incredibly dense concentration, or spike, of dark matter in its immediate vicinity. This spike would be far denser than the background dark matter halo. Now, if dark matter is made of a hypothetical type of particle, such as a WIMP, a weakly interacting massive particle, one of its key predicted properties is that when two of these particles collide, they could annihilate each other, transforming their mass directly into energy according to Einstein's famous equation, E equals mc squared. This annihilation would produce a cascade of secondary particles, including gamma rays, the most energetic form of light. If such a dense spike of dark matter exists around a supermassive black hole, the rate of these annihilations would be dramatically high. The energy released could potentially contribute to the total output of the active galactic nucleus. The tantalizing possibility is that some fraction of the high-energy gamma rays we detect from AGN might not be coming from the accretion disk or the jets, but from the silent annihilation of dark matter in the black hole's shadow. This would mean we are witnessing two cosmic power sources at once: the bright flare of ordinary matter meeting its doom, and the faint, ghostly glow of the universe's hidden component revealing itself through destruction. Testing this idea, however, is exceptionally challenging. The main difficulty is that the predicted gamma-ray signature from dark matter annihilation would look very similar to the gamma rays produced by well-understood astrophysical processes, like the interactions of high-energy particles in the jets. Astronomers are hunting for a unique fingerprint, a subtle bump or line in the gamma-ray spectrum at a specific energy that corresponds to the mass of the dark matter particle. Finding such a feature would be a smoking gun. The search focuses on specific types of AGN where the conventional astrophysical explanations might be weaker. For instance, a dormant supermassive black hole that is not actively accreting much gas would have a very quiet accretion disk and weak jets. If we were to detect significant high-energy gamma rays from such a sleeping giant, it would be a strong indicator that an alternative power source like dark matter annihilation is at work. The future of this research lies with the next generation of gamma-ray observatories, both on the ground and in space. These instruments will have the sensitivity to measure the spectra of AGN with unprecedented precision, searching for those tiny, telltale anomalies that could betray the presence of dark matter. While the dark matter annihilation hypothesis remains speculative, it exemplifies the creative ways astronomers are trying to solve the universe's greatest puzzles. It turns the most luminous objects in the cosmos into potential laboratories for studying the most invisible substance, suggesting that the key to understanding the dark side of the universe might be hidden in plain sight within its brightest beacons. Moving from the ghostly signature of dark matter to the grandest scale of all, we now confront a measurement so fundamental that any discrepancy in its value threatens to rewrite our understanding of the cosmos itself. This is the Hubble constant, a single number that quantifies the current expansion rate of the universe. For decades, astronomers have worked to pin down this value with ever-increasing precision, expecting different methods to converge on a single, universal truth. Instead, they have walked headlong into a crisis known as the Hubble tension, a stubborn and growing discrepancy that has become one of the most significant puzzles in modern cosmology. And remarkably, quasars are now entering the fray, offering a completely independent way to measure this cosmic speed limit, and their results are only deepening the mystery. To understand the tension, we must first look at the two primary methods that are disagreeing. The first approach builds a cosmic distance ladder from the ground up, using well-understood stars like Cepheid variables and supernova in nearby galaxies to calibrate distances and measure how fast those galaxies are receding from us. This method, championed by teams like the one using the Hubble Space Telescope, gives us a Hubble constant that reflects the universe's expansion as we see it today. The second method looks back to the very beginning. By studying the faint afterglow of the Big Bang, the cosmic microwave background, with exquisite detail as done by the Planck satellite, we can measure the properties of the infant universe. Plugging these early universe measurements into our standard model of cosmology allows us to predict what the Hubble constant should be today. The problem is stark. The local, direct measurements yield a significantly faster expansion rate than the prediction based on the early universe. It's as if you measured a sapling's growth rate for a year, extrapolated that forward, and then found the fully grown tree was much taller than your prediction suggested. Something doesn't add up. This is where quasars, with their unique properties, offer a third path, bypassing the traditional rungs of the cosmic distance ladder. The technique involves a specific and rare cosmic alignment, a quasar that is gravitationally lensed by a foreground galaxy. As we've discussed, this creates multiple images of the same quasar. But because the quasar's brightness is intrinsically variable, flickering over time, the light taking each path around the lensing galaxy arrives at Earth at slightly different times. This delay can be days, weeks, or even months. By carefully monitoring these flickers and measuring the time delay between the images, astronomers can calculate the extra distance the lagging light had to travel. This time delay is exquisitely sensitive to the overall scale of the universe, which is governed by the Hubble constant. Essentially, by knowing the time delay and modeling the mass distribution of the foreground lensing galaxy, they can derive a direct measurement of the Hubble constant that is independent of both the local distance ladder and the early universe data. The results from these quasar lensing experiments have been provocative. They have consistently produced values for the Hubble constant that lean toward, and in some cases even exceed, the higher values found by the local distance ladder measurements. This independent confirmation from a completely different technique is what adds such compelling fuel to the fire. It suggests that the discrepancy is not likely due to a simple error or a systematic flaw in one particular method. Instead, it points increasingly toward the possibility that the discrepancy is real and that its cause lies in our physical models. The Hubble tension might be the first observable crack in our otherwise incredibly successful standard model of cosmology, potentially hinting that our understanding of the universe is incomplete. What could this new physics be? The possibilities are as exciting as they are profound. Perhaps dark energy, the mysterious force driving the accelerated expansion, is not a constant as we have assumed, but an energy that evolves and strengthens over time. Maybe there exists a previously unknown type of neutrino or other relativistic particle that was present in the early universe, subtly altering the physics of the cosmic microwave background and throwing off our predictions. Another compelling idea is that our universe is not as uniform as we think on the largest scales, and that we reside in a local underdensity or void that is causing the expansion around us to appear faster than the cosmic average. While each of these ideas has its own challenges, the persistence of the Hubble tension, now bolstered by measurements from gravitational lenses around quasars, makes the hunt for an explanation one of the most urgent and thrilling quests in all of science. These distant, flickering beacons are therefore doing more than just lighting up the early universe. They are holding a ruler to the cosmos today, and the measurement they are giving us could be the key to unlocking the next great revolution in physics. But perhaps the most profound and elegant piece of evidence for an expanding universe comes not from measuring distances or redshifts, but from observing time itself slow down. This phenomenon, known as cosmological time dilation, is a direct prediction of Einstein's theory, and quasars serve as the perfect cosmic clocks to test it. The concept is mind-bending. As the universe expands, it doesn't just stretch the wavelengths of light, making them redder. It stretches the very fabric of space-time, causing time to appear to pass more slowly in the distant, and therefore earlier, universe from our perspective. To detect this, we need an event that has a recognizable duration, a beginning, middle, and end, and that occurs both nearby and far away. For supernova, this has been beautifully confirmed. The explosion and fade of a distant supernova takes longer from our point of view than a nearby one. But supernova are rare single events. Quasars, with their constant stochastic flickering, offered a much richer and more challenging dataset. For years, astronomers struggled to find the signal of time dilation in quasar light curves. Their variability is so complex and seemingly random that it was difficult to distinguish a genuine slowing of time from the natural irregularities of the sources themselves. It was like trying to prove that a distant drummer was playing a waltz in slow motion by only listening to a recording full of improvisational jazz solos. The breakthrough came from analyzing not individual flickers, but the overall statistical properties of the light curves across a huge sample of quasars. Researchers compared the light curves of quasars at different distances, looking for a specific signature. They searched for a characteristic timescale in the variability, the average time it takes for a quasar to make a significant change in brightness. According to the theory, this timescale should be stretched or dilated for more distant quasars by a factor directly tied to their redshift. A quasar with a redshift of 1, for example, whose light has been traveling for about 8 billion years, should have its variability timescale stretched to appear twice as long as an identical quasar nearby. After painstaking work, that is precisely what was found. The flickering of the most distant quasars, when analyzed in aggregate, does indeed happen in slow motion compared to their closer cousins. The ticking of these cosmic clocks is measurably slower, exactly as predicted by the expansion of the universe. This confirmation is monumental. It rules out alternative explanations for the redshift that don't involve an expanding universe. If the redshift of quasars were due to some intrinsic, unknown property of the light itself, as some had proposed in the past, then we would not observe this time dilation effect. The fact that we see time itself stretched provides a watertight, independent validation that the universe is truly expanding, and that the redshift is indeed a measure of cosmic distance and time. It connects the large-scale geometry of the cosmos directly to the local flow of time, a cornerstone of general relativity. When we watch the slow, stately dance of a quasar's brightness changes from the edge of the observable universe, we are witnessing the most direct possible evidence that we live in a dynamic, evolving cosmos, where the past literally unfolds at a more leisurely pace than the present. This intricate dance between the black hole's feeding and the galaxy's star-making leads us to one of the most crucial and complex relationships in modern astrophysics. It's a connection that challenges the idea of a black hole as a solitary monster and instead paints it as an integral part of its galaxy's life cycle. Across the universe, we observe a curious and powerful coincidence. Some of the most intense bursts of star formation, events known as starbursts, often occur hand in hand with the brilliant flare of an active galactic nucleus. A starburst is a galaxy-wide frenzy, a period where star formation kicks into overdrive, creating new suns hundreds or even thousands of times faster than in a normal galaxy like our Milky Way. To see this cosmic fireworks display of stellar birth happening simultaneously with the violent outburst of a quasar suggests a profound link, a shared trigger that sets off both of these incredible engines at once. The most likely culprit for this dual ignition is a galactic collision. When two gas-rich galaxies merge, it's a truly catastrophic event on a cosmic scale. The orderly motions of stars and gas are thrown into chaos. Vast clouds of hydrogen gas are compressed, shaken, and violently funneled inward toward the galactic center. This sudden influx of fuel has two dramatic consequences. First, the extreme pressure and density within these gas clouds trigger the rapid collapse that forms new stars en masse, creating the starburst. Second, a huge amount of this gas streams directly down to the very heart of the galaxy. piling onto the accretion disk of the central supermassive black hole. The black hole, suddenly presented with a feast, begins to consume the gas at a ferocious rate, lighting up as a brilliant AGN. In this scenario, the starburst and the AGN are siblings, both born from the same traumatic event. They are not directly causing each other. Rather, they are both effects of a common cause, the massive injection of gas from a galactic merger. However, the story doesn't end with their simultaneous ignition. The relationship between the starburst and the AGN quickly becomes a dynamic and often adversarial one. This is where the concept of feedback, which we explored earlier, becomes critical. Imagine the starburst is in full swing, converting the galactic gas reservoir into a brilliant young star cluster. At the same time, the AGN ignites, unleashing its tremendous power in radiation and winds. The energy from the AGN begins to interact with the very gas that is fueling the starburst. The intense radiation heats the gas, and the powerful outflows can blow it away. This creates a fascinating cosmic competition. The AGN, in its furious energy release, can actually quench the starburst by robbing it of its raw material. It's a case of the black hole effectively shutting down the star-forming factory that helped give it life in the first place. This negative feedback might be the key mechanism that prevents galaxies from growing indefinitely, explaining why we don't see galaxies with impossibly huge numbers of stars. Yet, there might be a more constructive phase to this relationship as well. Some theories suggest that the intense radiation pressure from the newborn stars in the starburst could actually help push gas toward the galactic center, further feeding the black hole instead of just blowing the gas away. Furthermore, the powerful winds from the starburst itself, driven by supernova explosions from massive, short-lived stars, could compress nearby gas clouds, triggering further rounds of star formation in a positive feedback loop. The AGN's own jets might also play a role as they plow into surrounding galactic gas. They could create shock waves that compress the material and initiate star formation along their edges. This paints a picture of a far more nuanced interaction, where the starburst and the AGN can sometimes enable each other, creating a complex, self-regulating system that governs how a galaxy evolves. Observing this connection directly is a monumental challenge, as the regions where it happens are often obscured by dust. However, astronomers have developed clever techniques to peer through the veil. One key method involves looking at specific infrared signatures. The dust heated by the young stars of a starburst glows brightly in the infrared, as does the dust surrounding an AGN. By carefully decomposing the infrared spectrum of a galaxy, scientists can estimate the relative contributions of the starburst and the AGN to the total energy output. In many luminous infrared galaxies, the products of violent mergers, they find that both processes are contributing significantly to the galaxy's brilliance. This co-evolution, with its cycles of feeding and feedback, is now seen as a fundamental chapter in the life story of a galaxy. It suggests that the brilliant, short-lived phase of a quasar is not an isolated phenomenon, but a transformative event, deeply intertwined with the galaxy's most prolific period of stellar birth, ultimately shaping its final size, structure, and future. And this brings us to our final, and perhaps most mind-bending, phenomenon, one that connects the colossal power of quasars to a fundamental paradox that threatens our understanding of reality itself. For decades, the study of active galactic nuclei has been about observing the incredible energy released as matter falls toward a black hole. But to confront the information paradox, we must consider the ultimate fate of that matter after it crosses the event horizon, and the strange quantum mechanics that might be at play even in these macroscopic giants. The paradox was born from a clash between Einstein's general relativity and quantum mechanics. General relativity, which describes gravity and the large-scale structure of spacetime, tells us that if you throw an object into a black hole, say, a book containing vast amounts of information, that information is lost forever behind the event horizon. The black hole's mass, charge, and spin might increase, but all the specific details about the book, the arrangement of its atoms, the words on its pages, are irretrievably gone from our universe. The problem arises when we introduce quantum mechanics, the rules that govern the subatomic world. One of the most bedrock principles of quantum theory is unitarity, which essentially means that information cannot be truly destroyed. It can be scrambled, transformed, or hidden, but it must in principle be recoverable. So, we have two of our most successful scientific theories in direct contradiction. Relativity says the information is lost, while quantum mechanics insists it must be preserved. This is the black hole information paradox. Stephen Hawking's famous work added fuel to the fire. He showed that black holes aren't completely black. Due to quantum effects near the event horizon, they should slowly evaporate over astronomical timescales by emitting a faint glow now known as Hawking radiation. The critical issue is that this Hawking radiation is predicted to be purely thermal, it's random noise, like the heat from a stove, and contains no information about what fell in. If a black hole eventually evaporates completely, disappearing from the universe, then the information it consumed would be truly and permanently lost, violating quantum mechanics. So how can the study of quasars, which are all about matter falling in, possibly help with a paradox about information possibly leaking out? The connection is not direct but profoundly insightful. While we cannot hope to detect Hawking radiation from a supermassive black hole, it would be unimaginably faint compared to the brilliance of the accretion. Disk theorists have proposed that we might study analogous systems. The incredibly hot, turbulent, and magnetized plasma in the inner regions of an accretion disk creates an environment of extreme physics. Some scientists suggest that the chaotic dynamics and shock waves within this flow could act as a kind of laboratory for studying processes that are mathematically similar to the quantum field effects that produce Hawking radiation. In these analog gravity models, the swirling, supersonic flow of gas creates an effective event horizon that sound waves cannot cross, mimicking the behavior of light at a real event horizon. By studying how information and energy are scrambled and transmitted in these chaotic plasma environments, we might gain indirect clues about how quantum information could be preserved or encoded in the radiation from a true black hole. The resolution to the paradox, which is still fiercely debated, might involve the information being encoded on the event horizon itself in an incredibly scrambled form, like a cosmic hologram. The intense fireworks of a quasar, the very process of accretion, could be imprinting information onto the black hole's surface in a way that is later released as the black hole evaporates over its immense lifetime. While we are far from a definitive answer, the fact that we can even pose such a question shows how quasars have transcended their role as distant cosmic curiosities. They began our journey as the most luminous objects in the universe, but they ended as gateways to the deepest questions about the nature of space, time, and information itself. In their brilliant, violent hearts, we find a testing ground for the laws of physics, pushing our understanding to the absolute limit and reminding us that the universe's greatest mysteries are often hidden in plain sight, written in the light of its most powerful beacons. As we stand on the precipice of a new era in astronomy, the future of quasar research is poised to be more revolutionary than at any time since their discovery. The incredible journey we've taken through these 25 bizarre phenomena is not a closed book, but merely the preface to a story that next-generation observatories are about to begin writing. With instruments of unprecedented power, we are not just aiming to solve existing puzzles. We are preparing to be astonished by questions we haven't even thought to ask yet. The James Webb Space Telescope, with its profound infrared vision, is already acting as a time machine peering back to the cosmic dawn. It is hunting for the very first quasars, the seeds of the supermassive black holes that now anchor giant galaxies. How did these objects grow so massive so quickly? Webb's ability to detect the faint, redshifted light from these infant quasars allows us to study their host galaxies in their formative years, testing whether they grew from the collapse of immense gas clouds or the rapid merger of early stars. By analyzing the chemical fingerprints in their light, we can trace the enrichment of the early universe, searching for the first heavy elements forged in the hearts of the first stars and distributed by the winds of these primordial quasars. It's a direct investigation into the origin of the cosmic structures we see today. Meanwhile, here on Earth, the Vera Rubin Observatory is preparing to conduct the Legacy Survey of Space and Time, a monumental project that will scan the entire visible sky every few nights for a decade. This relentless watch will transform our understanding of quasars from static snapshots into dynamic movies. Rubin's true power lies in its ability to catch change in the act. It will discover thousands of changing-look quasars, monitoring their dramatic transformations in real time, and finally revealing the precise mechanisms behind their shifts, whether it's a flickering central engine or a wandering cloud of dust. It will catch tidal disruption events in their earliest moments, giving us a front-row seat to the entire process of a star being shredded and consumed. Perhaps most excitingly, by measuring the subtle flickering in the light of millions of quasars, Rubin might be able to directly map the structure of the accretion disk itself through a technique called reverberation mapping on an industrial scale, turning each quasar into a laboratory for testing general relativity. And then there is the audacious square-kilometer array, a radio telescope network that will eventually span a continent, listening to the universe with a sensitivity 100 times greater than current instruments. The SKA will peer through the densest dust clouds to study the hidden hearts of Type II AGN, uncovering the complete population of active black holes that have eluded us. It will map the magnetic fields within relativistic jets with exquisite detail, tracing the flow of energy from the event horizon out to intergalactic space, potentially revealing how particles are accelerated to such incredible speeds. Furthermore, by observing the faint radio emission from neutral hydrogen gas in the early universe, the SKA will trace the cosmic web itself. When this map is combined with the positions of millions of quasars found by Rubin, we will see, in 3 dimensions, how these cosmic powerhouses are connected by the filaments of dark matter and gas, revealing how quasars shaped the large-scale structure of the cosmos. The synergy between these observatories, Webb's deep infrared eyes, Rubin's all-seeing optical gaze, and the SKA's penetrating radio ears will create a multi-wavelength portrait of quasars more complete than ever before. They are likely to solve the mystery of intermediate mass black holes, finding these elusive seeds in dwarf galaxies and globular clusters. They will provide precise measurements to resolve the Hubble tension, potentially forcing a revision of our cosmological model. But history tells us that every time we build a better telescope, we discover something entirely unexpected. Perhaps we will find quasars at even higher redshifts, challenging our models of the early universe. Maybe we will detect subtle signatures in quasar light that hint at the nature of dark matter, or even uncover evidence of exotic physics beyond general relativity. The coming decades promise not just answers, but a new universe of mysteries, ensuring that these brilliant, bizarre beacons will continue to captivate and challenge us for generations to come. Our journey through these 25 bizarre phenomena reveals that quasars and their active galactic nuclei are far more than just cosmic oddities. They are the universe's ultimate laboratories, places where the most extreme forces of gravity, magnetism, and high-energy physics play out on a scale we can observe from billions of light years away. From the illusion of superluminal motion to the dramatic transformations of changing-look quasars, from the self-regulating fury of disk winds to the precise cosmic correlations like the M-sigma relation, each peculiarity has taught us something fundamental. These objects are not isolated monsters, they are intimately woven into the fabric of cosmic evolution. The brilliant flash of a tidal disruption event gives us a front-row seat to the feeding habits of a dormant giant, while the faint absorption lines in a quasar's spectrum allow us to map the invisible cosmic web stretching between galaxies. They are the key to understanding how galaxies are born, live, and die, with their powerful feedback acting as a cosmic thermostat that governs star formation. They serve as standard candles to measure cosmic expansion, and their flickering light provides direct evidence for the stretching of time itself. Even their mysterious coronae and the bizarre broadening of ion lines let us test Einstein's theory of relativity in conditions impossible to recreate on Earth. Ultimately, the study of quasars is a humbling reminder of how much we have yet to learn. These enigmatic beacons shining from the edge of space and time continue to challenge our assumptions and push the boundaries of our knowledge. They force us to question the nature of reality, from the possibility of dark matter annihilation in their cores to the profound implications of the black hole information paradox. With every mystery we solve, a new, deeper question emerges, ensuring that these brilliant objects will remain at the forefront of astronomical discovery for generations to come. They are not merely distant points of light, they are active participants in the cosmic story, and in decoding their secrets, we come to a better understanding of our own place in a vast, dynamic, and wonderfully strange